Look, I'm just a geologist. I like rocks. I love rocks.
All right, everybody. Hello. Welcome to the Geology Flannelcast. My name is Steve.
Greetings, everybody. I'm Chris.
Salutations. I'm Jesse.
With the awkward silence. It's just
Yeah.
every week with the awkward silence.
Earlier today, I was like, I've got this one down, and I totally just blanked on it. Do you know, I forgot to mention this beforehand, so get ready. I'm going to surprise you all. Do you know what today we're recording this? Today is February 10th. You know what today is?
It's my dad's birthday.
Happy birthday. His birthday falls on National Flannel Day.
No!
Well, now it's funny. I was just telling Megan, my wife, I was like, I'm just wearing a t-shirt. I don't feel
we're
like
the same t-shirt.
nice. Yeah. I was like, I don't feel like going all the way upstairs and getting a flannel.
You got your Flannelcast shirt in the background.
True.
Yeah.
That's true. And my mug. I don't know if you can see the mug.
I see in the very background. Yeah.
It's like a little Easter egg, except I just pointed it out, so I guess it's not really an Easter egg.
All right. Well, everybody, welcome to the premier geology podcast, the Geology Flannelcast. We are three geologists that aren't scared to tackle the topics that nobody else dares to touch.
Or maybe they dare to, but just not in podcast form.
Whatever. We'll go with it.
Exactly.
It's our tagline, so.
Yeah.
I love it. I love it.
All right. We got a little news story. So, well, I guess before we get into this little news story, we're just going to spend a couple minutes on today. The topic of today's podcast is all about sandstones. We're going to try to cover. This is a huge topic, so we're obviously not going to be able to cover everything, but we're going to have some fun with this. Sandstones are my personal favorite type of rock. Just FYI. So,
Really?
I love them. I don't know. Some people might say they're boring, but
No.
I kind of admire the simplicity. There's a complex simplicity behind sandstones.
That's how I feel about coal.
Good. Maybe we'll do 3 episodes on sandstones.
Yeah, we could definitely.
Cool. I mean, absolutely. We could do yeah.
Well, now I'm feeling all kinds of pressure to pick my favorite rock.
Pick a favorite rock.
I don't. Next topic.
There's a good. I want to say that there's a textbook. I don't know if it's good actually, but there's a whole like giant textbook, and I want to say it's called like Sandstone, or it's called like Sand and Sandstone. So you could have a whole textbook on this topic. That's how.
I think I have that textbook. In fact, I know I have that textbook
By Pedestrian, I think that's.
Yes. Yeah. I got that.
Yeah, that's a good one.
Yeah. So we will be covering the intro to geology sandstone topic today.
No. We get a little more in depth into that than
you're right.
intro.
You're right.
But anyways, let's before we get into that, we got a little cool well, it's an unfortunate news story.
Yes.
Yeah.
So
Unfortunately, well, not unfortunately. Last week we covered glaciers and all things glacial related, but unfortunately, in the news in the past week, there was a pretty tragic event.
So, do you want to?
No, go ahead, Jesse.
Okay.
I was throwing it to you if this was a newscast.
I thought so. Yeah. So, right on the Indian border with Tibet, Nepal, up there in the Himalaya mountains, a piece of a glacier actually broke off and fell into a river and caused basically a flash flood. It sent a pulse of water, and unfortunately what was downstream was a dam, and the pressure of this water from this flooding broke the dam, which then flooded the valleys downflow. It actually ran into a second dam, which also broke.
Oh my goodness.
And it ended up there's a few hundred people missing, and a couple dozen were killed. But it's something, it's an interesting, because we didn't really get into this too much. It's what's called a hanging glacier, which is a normal valley glacier runs, as the name implies, like these alpine or mountain glaciers that run along the bottom of the valley. But you can have these smaller glaciers that are higher up, and they usually run into the valley glacier. They're like glacier tributaries, but they sit at a higher elevation. And there's a number of reasons you can get them forming, but in which I won't get into. But in this case, what had happened was there was a landslide that hit the front part of this hanging glacier. And it was the front part's probably the weakest of the points, because it's where you're starting to get a lot of melt, and especially in this part of the world, a lot of these glaciers are melting and receding. So it's there's some inherent weakness there. So this landslide of rock hit the front end of this glacier, and it caused a massive piece of the glacier to break off. And so now you had this rock and ice mixture that went down slope and into this river. And so it caused this flooding down flow. Yeah, kind of scary. There's some video out there, maybe we'll post. They did recently just rescue a few people. They're building, the one dam was this hydroelectric plant they were building, and a lot of the workers were in the tunnel into the side of the valley, and the floodwater rushed into the tunnel, and they ended up luckily a significant number of them got to the escape ladder, which was like the top of the tunnel, 14 feet, and the water rushed into like 12 feet. So they
wow,
fairly, and then they had to take this escape ladder something like 1,200 feet to the surface.
oh jeez,
Holy cow!
Yeah. So it's it's an interesting story. It's a sad, very sad, obviously, but
yeah,
I think on one hand, it's sort of like this, freak event, but on another, with the climate changing and things getting warmer, you might see more of these, I don't know, glacial destabilization events. So
yeah, I was just while you're talking about that, I was kind of just briefly skimming through. There's a New York Times article talking about this, and I'm going to post this on the Flannelcast website. But that was the one thing they were talking about, is that, just as things warm up, these glaciers become more unstable. And this is just, kind of the things that you're going to have to start dealing with more and more. And then it's just kind of just the fact that the other thing that I want to talk about is when these dams break. I guess this is more of an engineering type of thing, but that's really bad when a dam breaks. I mean, that's just total devastation. Just imagine just a giant flash flood coming down at you with absolutely potentially zero notice. And there's been some really bad dam failures over the years that have happened that have just completely decimated towns. And it's just, man.
There was one in
Italy had some really bad ones.
Johnsonville. Johnstown, Pennsylvania, where like 14,000 people died.
So the guy that engineered the dam for the Johnstown flood, or when the dam broke there, he also was involved with engineering another dam that bursted, that broke. Yeah, so he had like 2 failed dams on his on his resume.
Not bursted.
The bursted dam.
The burst.
Yeah, it was an earthworks dam.
Yeah,
and it was at like a private club for rich folk, and it was one of the things that led Andrew Carnegie to really get into philanthropy, because I think he was a member at the club, and he sort of saw the devastation.
Because Carnegie was he based in Pittsburgh?
Yeah.
Carnegie Mellon, and
So and then Johnstown is like
Not
an
far
hour
from Pittsburgh.
From Pittsburgh.
Yeah, probably something like that. Yeah. Pitt has a campus in Johnstown.
Yeah.
Okay.
Pitt, Johnstown. Yeah. So close to 3,000 people died. One of my friends I grew up with, his great grandmother, I want to say it was a great grandmother, was it was a young child, and she was pulled by her hair out of the floodwater.
Oh,
So that's their family story.
My goodness. Holy shnikes.
Yeah. Was it 3,000? I thought it was like something crazy, like 14,000. I could be wrong.
Yeah. it was the largest until Galveston, which I think
Ah.
was like 13.
Okay.
Well, 3,000.
Astros.
Oh yeah, for Johnstown.
But yeah, so we just want to address that, especially since we covered glaciers last week. We didn't want to leave this, our hearts go out to all those people, but yeah, it, crazy stuff, climate change.
Yeah.
Am I right?
It's
I'll get
Yeah.
you.
Yeah.
Not-
So check out the news article that Chris is going to post. Thanks, Chris, on
Thanks, Chris.
geologyflannelcast.com.
Real fast. Johnstown we said 3,000. It's 2,200. Just FYI.
Ah,
Oh wow, it's way off.
It actually is pretty crazy when the dam broke, it had a flow rate that temporarily equaled the average flow rate of the Mississippi River. It's a lot. That's
a lot of water for something that's not
Yeah.
not expecting that much water.
May 31st, 1889, Johnstown, Pennsylvania, Western Pennsylvania. But
That's
All
the
right.
year I was born.
you're born 1889. That's
Yeah.
make you the oldest person on earth right now.
in Johnstown, Pennsylvania.
Yeah, actually, probably.
Anyways, so ladies and gentlemen, the topic today is on sandstones. Like I said, this is my personal favorite rock that there is. This is my favorite.
Okay,
So
that's it. Well, we'll see you next week.
Yep.
spelled SANDSTOND or STONE. Excuse me. Jeez.
Wow.
Wow.
Ah,
Woo. So all right. So when we get into sandstones, I guess the first thing we want to talk about is the type of I guess the category of rock that sandstone falls under. So sandstone is a sedimentary rock.
wait,
And-
it's not classic punk or hard.
I liked it. I
I'm
thought
gonna,
it
I purposely left that silence there because I'm gonna insert cricket sounds.
Come on, the three types of rock.
yeah.
Yeah.
Anyway, yes, igneous, metamorphic, or
Sedimentary. Very good.
Yeah.
Yeah.
I once worked with a guy who thought it was cemetery rocks.
Cemetery rocks.
Yeah.
Aren't those called gravestones?
No, he literally thought it was igneous, metamorphic, or cemetery, the kind they make tombstones out of.
They used to use limestone.
For
That's true.
tombstones.
Yeah.
Yeah.
that's-
Yeah, it didn't really work out too well. Did it?
No, that's
No,
why.
those are the ones that are all melty.
Yeah. All right. So sandstone. This is a big topic. So let's start off at the very basic and work our way up from there. All right. So sandstone is a type of sedimentary rock. So, for all intents and purposes, there's two main categories of sedimentary rocks. You have your clastic sedimentary rocks, and your chemical, also known as biochemical sedimentary rocks. Sandstone falls under the clastic sedimentary rock. So what that means is that these classic sedimentary rocks are dominated by the mineral quartz. Quartz is a very, very strong mineral. You can't get rid of this stuff. It's just it just hangs around forever.
It's very stable at Earth's standard temperatures and pressures.
Yes.
So it doesn't
Yeah.
break down very well.
Yeah.
It forms at low temperature, so it is stable at low temperature.
Yeah.
Yeah.
So this stuff, these classic sedimentary rocks, they tend
Well,
to follow.
what does the word clastic come from? Come on, buddy.
Oh, I see. You have a little
I-
note.
I-
Here. I did not know this until
Yeah.
I
Clastic
Oh.
comes from klastos, from the Greek, meaning broken.
Clastos sounds like a villain.
Yeah.
Like
Yeah,
a
right?
comic
Doesn't
book
it?
villain. He will break your bones.
We should start making geology comic books.
Oh my goodness.
Ugh. Forget
So-
podcasting. Comic books is where it's at.
If only I was artistic.
Yeah. If only I could write.
Yeah.
All right, podcasting it is. Carry on.
So what classic sedimentary rocks are? They follow this kind of this outline of you start eroding down, you start weathering down pre-existing rock. So I'm going to go with a textbook case here. Start off at like a mountain range. All right. We've talked about this on the podcast before. Mother Nature wants everything to be flat. She hates topography. She hates high topography, and she hates kind of low-lying topography. She wants to fill the low-lying stuff in. She wants to break the high the high standing stuff down.
The great equalizer.
Exactly. She's really bored. She just wants everything to be Kansas, and I don't understand it. I love the mountains. The mountains are always close to my heart.
There's mountains in Kansas.
What? That's getting edited out.
Yeah, Mother Nature driven by gravity.
Yeah,
Just pulling her down.
so Mother Nature starts attacking the mountains, right? The mountains start getting, as soon as the mountains get lifted up, they start getting broken down, right? We have things like frost wedging. So ice, you have water getting into like the cracks of ice. That's one of the main culprits for breaking down mountains.
So real quick. So when water gets into cracks and then the sun goes down and it freezes, when water freezes, it actually expands. It's one of the few materials on the planet that actually expands when it gets colder. Most things, when it gets colder, it actually shrinks. But water, because of the way it crystallizes, it actually, the bonds actually open up a little bit. And so in just that little bit of opening up, it actually has enough force.
It's really strong when it expands
to crack the rock.
Yeah.
That MacGyver episode where he poured water into a crack and then shot it with a CO2 fire extinguisher, and then it broke the rock. So if MacGyver can do it.
I would like to look at that. I've never seen that episode, but it sounds like he would need a lot more time to do that. Because
once it freezes, bam.
Well, so water expands about 9% when it's frozen. All right. So if he just had a little, I'd have to look at this crack. I mean, number one,
the rock was on the verge. All right.
Okay, it was on the verge. Okay.
Yeah.
So
anyway, carry on.
So we're talking about frost wedging, and we got a long ways to go to make a sedimentary rock right now. So just imagine during the daytime, the temperatures are high. They're above, let's just say above freezing, right? And the water kind of gets into these cracks of the rocks. At nighttime, things go down, below freezing. The ice expands and maybe it cracks the rock a little bit more. Daytime comes around, that ice melts, maybe it goes a little further into the crack. Nighttime, it freezes and expands a little bit more. So over thousands and thousands of years, hundreds of thousands of years, or whatever,
or one MacGyver episode,
it really starts to have an effect, and it really starts to break down your rocks. And so that's called mechanical weathering, right? And it's type or physical weathering, and it's basically you're making little rocks out of big rocks. The big rocks being the mountains, and little rocks being the sediment that eventually the mountains get broken down into.
And a lot of times with physical or mechanical weathering, the pieces, the clastos that you have,
I like that.
They retain the physical properties of the parent rock.
Yeah. It's just little pieces of the big rock.
You can usually tell where it came from.
Yeah. So we start doing that, and we start breaking this stuff down. And then when we break these big rocks down, we call this sediment. So now there's a lot of water on Earth, and most of the times the sediment is being moved by water. Not all the time, but you can have stuff being moved by wind, or I guess glaciers, but that's technically water as well, if you want to look at it that way. But most of the times you start to
water.
It's ice.
It's H2O, but it's not water.
All right, I'll give you that.
It's lava. It's not a rock, right?
All right, we're not going there. So anyways, the whole point I'm getting the stuff starts getting transported, and some of the stuff can get transported pretty far, and sometimes doesn't. The sediment doesn't get transported very far at all. And we'll talk about that with different types of sandstones. You can look at a sandstone and figure out how far the sandstone's been transported, how far it's been moved along. All right. So you transport your sediment X amount of distance, however far it is, but you can't transport this stuff forever. Eventually it's got to stop being transported. So I always like giving this example of, so say you have some sediment, it flows into the Mississippi River, right? The Mississippi River flow, you're in Minnesota, the headwaters of the Mississippi River, and it flows all the way down to New Orleans, right? Hits up Mardi Gras, and then it flows into the Gulf of Mexico. Well, the Mississippi River doesn't really flow that far into the Gulf of Mexico. Once it hits the Gulf of Mexico, it starts to kind of disperse and diffuse into the larger standing body of water. So what ends up happening is that as that water kind of diffuses into the Gulf of Mexico, it loses its energy and it just dumps off all of the sediment that it brought down. And that's how the Mississippi Delta formed over time. Like half of Louisiana is made of it's part of the Mississippi River Delta, give or take. So you deposit your sediment eventually. The sediment can't transport forever. All right. And then you deposit it, and this sediment tends to get deposited in low-lying areas, right? Low-lying area, like the Gulf of Mexico, for example, right? We call this a basin. So your sediment gets deposited, and then more stuff gets deposited on top of that, and then over time it gets buried and then compacted. And then the next step to make a sedimentary rock is that your unconsolidated sediment has to then get cemented together to form like a cohesive rock or cohesive rock formation. And that's where groundwater comes in. Groundwater percolates through your sediment, and inside that sediment, there's pore space, and the groundwater that's percolating through starts to precipitate out minerals in the pore space, and that forms your cement. And that's the whole process.
Yeah. In regards to sandstone.
Yes.
Sometimes, so like Chris said, you have your weathering, your erosion, your transportation, your deposition, and then lithification. Now with sands and stuff, you can only squish it so far. Like you can only squish it like 10%, 20% maybe. If we're not talking about this episode, but like your clays and your silts, they can get squished down like 50 to 80%. Basically, you're squishing out all the water, you're squishing out all that extra space. But because you have these sand grains, and if you're watching on YouTube, you can kind of see my hands, they can only squish together so far. And then the lithification part, like the cementation, like Chris was saying, that's where the groundwater comes in, starts bringing in all these ions and other schmutz, essentially the glue, if you will.
Schmutz,
Yeah.
that's a good term. I like that.
Yeah, a lot of times the quartz grains too, depending on how far they travel, as they're getting weathered, they become rounder and rounder. And so that's part of the packing issues. You have all these little round spheres, and so they don't pack down. There's a lot of strength there. So they're strong to begin with because it's quartz, but they don't pack down as
yeah. If you've ever seen one of those like decorative vases with those glass beads in it,
yeah,
or marbles or whatever, like if you look at it, there's a lot of empty space in there.
Oh, I like that.
Yeah.
It's something like 72% is solid, so which leaves a good amount of open pore space, a lot of like interconnected empty, in that vase scenario, it's air.
And that's part of it, is that they're connected.
Mm-hmm.
So there's space, but it's also connected so the water can get through.
Mm-hmm. So if you were to fill that vase with water, it would fill up pretty easily. It wouldn't like bubble up and like get stuck in spots or whatever.
I was going to say, if you're at the grocery store, look at the bin of apples or bin of oranges, but
Ooh.
Decorative vases, we run in different crowds, I guess.
I
definitely don't do as much grocery shopping as I should. I just spend my time in Pier 1, apparently.
Yeah, vase shopping though, or vase shopping.
Yeah, Megan, you go buy the steaks. I'm gonna go. I'll be at Pier 1.
I get a new seasonal decorative vase.
Exactly.
All right. So that's kind of the general breakdown of how a sandstone forms. So there are things called we have here on the outline chemical sedimentary rocks, where that's more or less like they're being formed as a byproduct of chemical reactions, whether it be like oxidation or something like that. So we're not dealing with that kind of stuff here. I always kind of view as like these like chemical sedimentary rocks as like it's almost like a very delicate process with these chemical reactions. The classic sedimentary rocks is kind of like Hulk smash, like boom, you break up these mountains, you push them down, transport them far, and it's just very, smash them up.
And to be honest, there is a lot of interfingering of these as well.
There,
Like,
yeah, you
sometimes
always get a little bit of chemical reactions occurring with this stuff. Yeah,
exactly. And or with the chemical reaction stuff, sometimes you get an input of this classic material as well. So,
Mhm.
they can intermix, and they often do. There's, just like anything in nature, it's very rarely like a very typical something perfect. So
we're trying to keep this simple though. So
Yeah.
let's just, but yeah, you're right. So, all right. So now we got this sedimentary rock, and your grains just we're just going to talk about sandstone, right? So depending on what type of sandstone you have, we'll get into the different types of sandstone. They're made of these individual grains that are sand. I guess we should go over. We don't have this in the outline, but a sandstone is made of sand-sized grains. So the definition of sand is a particle of sediment that has a diameter between 2 millimeters and 1/16 of a millimeter. So there's no like special definition for sand in geology. It's all it is just a size category. So, most of the times when you're dealing with sandstone, quartz is going to be, I think we mentioned this before, quartz is going to be your dominant mineral, but you can get other minerals in there. We'll talk in a couple minutes about like feldspar. That's a very common mineral. It's also a very important mineral when it comes to sandstones. And then sometimes you can also just get these things called lithic fragments. And it's just a chunk of pre-existing rock that's in that sand size category. So those are like kind of like the three heavy hitters when you're dealing with sandstones.
Now, yeah, when you go from 2 millimeters all the way down to 1/16 of a millimeter, that's a large size range.
Yeah.
So depending upon that size range, 2 millimeters is like rough sandpaper. 1/16 of a millimeter is like
barely visible.
Yeah. I mean, you can still feel it with your hand. It's not like a sheet of like copy paper or something, but it's you can still feel it with your hand, but it's I guess it's smoother than like a nail file, but
it's
not much smoother than a nail file.
For all intents and purposes. 1/16 of a millimeter is pretty much like that's kind of the cutoff point that the human eye can see. So then the next size is smaller than that is silt, and you really can't see. Generally speaking, you can't see the individual silt size grains. It's too fine.
Right, but then how well Mother Nature sorts these grains will that's gonna change your sandstone a lot. So if you have a constant level of energy, say you have a constant stream of water going at a constant speed that can only carry 2 millimeter sand grains, that's great. So then the only thing that's getting deposited in this theoretical basin is going to be 2 millimeter sand grains. So these 2 millimeter sand grains are just going to keep getting deposited. Think of like a beach or something like that. The energy is always pretty much close to the same. It's always carrying these 2 millimeter sand grains. That is what you call well sorted.
Mm-hmm.
Now, for those engineers who are listening, we call this poorly graded.
All right. Next, just stop it. Just stop it.
Are we not catering to the engineers?
No, we're not. This is a geology podcast. All right. Don't even plant that seed. All right.
Sorry, I've had so many arguments about this, especially early in my geologic career. Like, I would write poorly sorted, and then the engineer would be like, "No, this is well sorted," and I'm like, doubting myself because I was new and like, no, these are all the same grain size. I don't understand. It's poor. It's well sorted. Like, and then getting all mixed up in my brain and back and forth and all this stuff. So well sorted means everything is the same size. Poorly sorted means there's a bunch of different sizes.
Mm-hmm.
And then if you want to know about the engineering scale of graded, poorly graded, well graded, send us an email at geologyflannelcast.com or write us a comment on the YouTube page. First subscribe, then send us a comment. And then we can, if we get enough comments about this, we can discuss it. But yeah, so depending upon how well Mother Nature sorted your grains depends on basically how much pore space you have. So if you take my super awesome metaphor of our decorative vase, right? If you have all, say, super ball sized marbles in your decorative vase, right? You can imagine there's a lot of empty space in there, correct?
Okay.
Yeah.
And let's say you take that super ball size and you drop it down to marble size. Well, believe it or not, there's pretty close to the same amount of empty pore space in that vase. Now, there's probably a little less, but
No, there's more. The smaller the grain size, the more surface area.
yes, I'm sorry, more.
Yeah.
Which kind of seems counterintuitive. But then if you take those super ball size marbles and you take those marble size marbles and you mix them together and put them in that vase, all of a sudden, all that empty space drops down
See ya.
a lot.
Yeah.
And then if you do that, not just with 2 different grain sizes, but with 3 or 4 or 5 or 6, basically you're taking all that small stuff and you're filling in all that airspace.
Mm-hmm.
So depending upon how well Mother Nature sorted your grains depends on how much pore space you have. And pore space is huge when it comes to drinking water or oil and gas, or like there's a million, like that pore space is critical to so many things.
So I'm going to deviate a little bit. All right.
No.
A little bit.
We were so on track.
No, we're doing a good job, but this is really interesting. And I think this is a cool thing to talk about.
Yeah.
We talk about porosity, but Steve started hinting at the topic of permeability.
It's my favorite.
Oh man, who doesn't like a good permeability discussion?
Permeability and also connectivity.
Well, let's go over. So, okay.
Not conductivity, connectivity.
How does permeability differ from permeability? Enlighten me.
Wait.
There is a difference. Permeability.
Well, let's explain what permeability is first.
All right, go ahead.
Okay. So
Continue.
Thank you. Okay. So we got all this pore space, and like Steve said, groundwater is super important. That's a huge source of fresh water for people. So, but what groundwater percolates through the sediment, and it's moving through the pore space between sediments, right? So you can actually have a lot of pore space, but not. Well, the permeability means how well does the groundwater flow through your sediment. And you can actually have a lot of pore space, but have poor permeability. Like I think Jesse was kind of hinting at this earlier with shales, right? So shale, this is a different podcast topic, right? We're talking about sandstones today, but I'm gonna
talking about sandstone, not shale.
Sandstones. Talking about sandstones.
Talking about sandstones.
I think of that Allen Iverson.
That's what I was
talking about. Practice.
Talking practice. But we're talking about but with shale is made of clay-sized particles, and there is a lot. What's the pure porosity in shales? Like 75%?
Yeah, you can get above 50. That's a classic.
50, yeah.
Intro when you teach like porosity, you're like, all right, I have a sandstone that has 30% porosity, so it's 30% open space, and a shale that has 50% open space. Which one do you want to hold your water? And of course, students are like, oh, the one that has more. I'm like,
well, you can't suck it out then.
Yeah, it holds more, but you can't get it out.
Yeah, well, that's also because of the clays tend to be platy, and it kind of slows down the flow of water. It's really hard to get water to flow through these platy clays, whereas sand or spherical, they tend to be spherical, spherical grains, and it's a little easier for water to flow
decorative vase.
Decorative vase. There you go. So there you go. So porosity versus permeability. They don't, just because you have a lot of pore space doesn't mean that the water can easily flow through that pore space. Yeah. All right. So did you want to talk about connectivity?
So basically permeability has more to do with flow through. Connectivity has to do with how well the network of connection is. So you
Okay.
can have a zone of permeability where you can have flow through, but connectivity has to do with the network of connections. So very, very similar.
Okay. So
Yes.
So it could be like one pathway versus.
Yes.
Got it.
Exactly.
all right. So let's get back to the sandstones now. I'm looking through this. Where
We're at uses.
are we already down there? Okay.
Yes.
Well,
No, we're formation still. You're talking about like. Do you talk about
Yeah.
erosion
So there's just these two terms we go back to.
Oh, yes, erosion. Yeah, we can get more into erosion. Sorry.
Kind of bounce it around a little bit. So we're talking about, kind of breaking down these big rocks to make your sand or your sandstone. We have these two terms, and a lot of people, and I'm not gonna lie. Before I went, I started learning about this in school. I thought that weathering and erosion were the same thing, but there's a subtle difference, right? Weathering is just kind of the breaking down of this material, right? Of your rock, right? And erosion, you remove the material and then you transport it and you take it away. So there's a subtle little difference between.
and actually, there's like there's a difference between erosion and transport.
Right. Yes.
Erosion is the removal, and transport is when it starts. So it's like weathering breaks it. Erosion is when it like leaves that parent rock. This is into the weeds of some.
Yeah.
Yes. Yeah. Because honestly, weathering, erosion, and transport, in intro is kind of just like you break the rock and you move it.
Yeah.
Weathering is like the process of separating it. Erosion is kind of just moving it away. Like weathering could be like the crack. Erosion is it falling away, and then transport is it actually being moved by some other mechanism,
fluid or gravity mobilized,
or air, or
air is a fluid.
Stop it.
Yep.
This isn't a physics com.
That's strike two against the engineers. All right.
No, you're right. Fluid. Yes. I thought you meant liquid. I do that a lot. When someone says fluid, I think liquid.
A lot of people do. Yeah.
I'm teaching hydraulics in my sedimentary class right now, so it's the only reason I know.
No, you're right. Because you were correct. I do that all the time where I think, oh, fluid.
Yeah, I mean, ice
must be water.
Yeah, ice is a fluid.
Yeah,
anything that has fluid flow.
So, well, let's move on to this. So, while we're talking about transportation, moving the sediment along, you can get into this this term called maturity or sediment maturity.
Hang on, we're still on erosion.
Oh, I thought we finished erosion.
No, erosion. Yes, erosion. We're talking about the process of separating the rock from the regolith, but process of erosion could be abrasion, right? Other rocks rub against it. It could be plucking, in that a grain actually gets plucked out of the matrix. You can get scouring, which is kind of like a
digging down,
sandblasting-ish thing, and it can be from wind or water. Or, in the case of chemical sedimentary rocks, dissolution. You can actually like dissolve the rock,
sinkholes,
into its ions, and then it gets transported away and then redeposited somewhere else. So that's kind of, so weathering is like the physical, like just breaking. Erosion, again, abrasion, plucking, scouring, dissolution. Those are just examples. I'm sure there are more, but then once it gets abraded, plucked, scoured, or dissoluted.
Oh, yeah.
That's a word.
It's very good.
Then it has to go somewhere, and to go somewhere, it's
transported. Is that what we're getting at?
Yeah.
All right.
Yeah. So now we're at transportation.
Yeah. So most of the time, when your sediment gets moved along, it's being moved by water. There's so much water on Earth. Water's everywhere. You can't get away from it. But it doesn't have to just be water. You can have air moving sediment along. You can have ice. We got into this little disagreement early in the podcast about water versus ice. What else could move? Gravity can move
Gravity,
sediment along.
free fall if you have
Rock fall, something like that. But yeah, so that's gonna just move your sediment along. But so when your sediment's being moved along, we have this thing called sediment maturity, right? And so I know we didn't even really get into the sandstones yet, but there's a huge backstory that we have to tell before we can be like, okay, these are the types of sandstones, and this is what this is. We're trying to paint a picture here. Right?
Maturity plays a big role in this, so
yes,
get ready.
So maturity.
I don't have much maturity.
Yeah, you stole my joke.
Sorry.
It's something that none of us really have, right? This podcast lacks.
I don't know. I am rounded.
Steve's
got possibly well sorted.
He's got multiple decorative vases.
There's a lack of never mind. Okay, so sediment maturity. So you can think of this as like the degree of working the sediment. All right. So what we're talking about, basically it's a spectrum. We have two ends of the spectrum: mature sediment and immature sediment. So let's talk about mature sediment first. Mature sediment is we have rounded grains. It's all well sorted. That means all of the grains that are together are all roughly the same size or pretty close to the same size. And the grain size is sand size, so between 2 millimeters and 1/16 of a millimeter. And so this stuff tends to be quartz. Like, just if you have a very mature sediment, it's all rounded, the same size, sand size quartz.
And well, does size matter?
It tends to be sand size, because like if you have something like a conglomerate, which is like next size up, that doesn't tend to be mature.
Oh, that's interesting.
We didn't really. I just want to touch on this quick because you keep giving the numbers of 1/16 or whatever, and I don't know what any of that means. None of that. It's all meaningless to me. But we break down within sand, like we said, there was a big range, and I don't know if we mentioned this or not. We break down sand into sub-classification of very fine, medium, and coarse, and very coarse, depending on, so when, a lot of
bring that very coarse into here.
I know, sorry. VC, you gotta be very coarse. But it's a way, because a lot of times when you're determining grain size, it becomes somewhat of an art form of being able to eyeball it. So I just want to.
It is an art form. It's
yeah, and you have grain size charts, these little handheld cards.
Mm-hmm.
And
I have one in my wallet.
Yeah, some of them. I bet you have the transparent one, right?
Yeah, I think so.
Yeah, and some of the classier ones actually have the grains glued onto the card.
Oh, I did. I used to have one of them, but it doesn't fit in your wallet.
The transparent ones are nice.
I'm
I don't.
probably going to call myself out on this.
It's in my field book. But I just want to mention that. So when we think about grain size, we talk about fine sand or medium sand or coarse sand.
And like Chris said, the degree of working. You think about like anything you've ever broken in your life. I'll
be here all night.
Lots of things. Yeah.
You shatter something, like you shatter glass, and it's all sharp edges and jagged and ouchy, right? And
ouchy.
But then if you've ever seen, come on, it's a technical term. But then you've seen things like sea glass that they sell also at Pier 1 for your decorative vases. It's all well-rounded. Like,
sponsored by Pier 1 right now? Is that
we should be.
Well, are they still in business?
Actually, that's a good point. But you know who is in business? The formatting formula.
Yeah, there we go.
That's right. Formatting formula I'm gonna get an angry email saying like, why don't you just have Pier 1 sponsor your podcast? But no, honestly, that was a terrible segue. But honestly, the formatting formula, formattingformula.com, YouTube/C/formatting formula for all of your Word documenting needs. They just posted some new videos this week on YouTube.
I'm updating this document right now, and it, a table of contents and whatnot, and it's like 300 and some pages, and so I kept the link from the table of contents to where I was going. I have to get back to the table. I was like, I know there's a trick where I can put a button to take me back.
The back button.
But I couldn't find it, and then like I needed to have it finished. I was working on it on like Sunday and needed it for like Monday, and I was like, next I'm gonna need to redo this document in a couple of months. So I am definitely hitting up the formatting formula for this purpose. I'm gonna have them make it look really nice. It's for my contract renewal. So
nice.
Yeah. So I want to have them polish it up, and I need to find that back button.
Yeah, but honestly, the formatting formula. So Jesse's referring to this back button. You can customize your toolbar at the top of your Word documents to be set up however you want it to be set up. I had no idea. I thought like that's the way Word sent it to you. That's the way it has to be. Nope. Formatting formula taught me how, like, you have your undo and your redo button that just comes standard. Well, they gave me a back button, so I can go back to that point of the document where I was, whatever I was working on. And I'm not going to lie, when you're working with large documents, it's a time saver, especially if you're doing like searches or finds or whatever. Like you find it and then you're like, okay, well, but where was I before when I was working on this? Boom, back button, bam, back 200 pages, done. So the formatting formula's genius is just, it is unbelievable. So can't say enough about them. Formattingformula.com or YouTube/C/formatting formula. And we'll give you an update on Jesse's promotion package.
All right. So where are we at? Steve, you're talking about sea glass.
I was thanks. Couldn't have just said roundedness or weathering, but no, you had to say sea glass. Yes. So when you break a piece of glass, it's very sharp, but when it gets rolled around and rolled around and rolled around, perhaps in the sea, it gets rounder and rounder and rounder and rounder. Mm-hmm. Because like Chris said, Mother Nature doesn't like anything tall or pointy, so it's going to keep knocking off those edges. And
that's yeah, so it's called spheroidal weathering, and it's just because the corner of an object has your most exposed surface area.
There you go.
3 faces on a corner, so that's going to weather first because it's pointing out.
It's going to keep getting knocked off. That aspersion is going to keep getting knocked off, and eventually you knocked off all your aspersions, and all you have is a round marble, like in your decorative vase.
That's a good word right there.
Aspersion.
Aspersion. Yeah,
I like it.
You know how I found that out? I hit the synonym button on Word, thanks to the formatting formula.
Oh,
that's right. You can type something in, and then just hit synonym, like you're typing something you're trying to sound fancy, or it sounds too fancy. You want to dumb it down a little bit. You can go that way too. So anyway, another little plug for the formatting formula. But carry on.
All right. So I think we talked about maturity. So sandstones are going to tend to be more, well, I shouldn't even say this. You want to look at the sediment and figure out if the sediment's mature or immature, because mature sediment, like I said, just to kind of recap, everything's rounded, well sorted, and you get a lot of sand-sized quartz. That indicates this thing's been transported pretty far. All right. And Mother Nature's had a chance to sort it all out. All right. Get rid of like the weakling minerals, things like mica, the feldspars, anything that's just not as resilient as quartz. Get it out of there. So it's been worked a lot, and we just kind of stuck with the rounded sand-sized quartz. Immature stuff means that your sediment, your sediment hasn't been transported like relatively far at all. It's pretty close to the source where it came from. So that's going to be really important when we want to check out the provenance, or the origin of your sandstone, of the sediment within your sandstone. So we'll get into that in a couple minutes. Moving on, we deposit our sediment. All right. So we talk about sediment gets deposited in some type of basin.
Right. Somewhere where the energy of your system slowed down.
Yep.
Most likely water, but it could be anything. Could be wind too, or ice melt. But somewhere where the gradient slowed down, meaning like the slope of your hill for the water leveled off, and therefore it slows down and just drops the sediment.
Yeah, it just the system starts to lose its energy. Like think of like a river flowing into a larger body of water. Like the Mississippi River doesn't just keep on flowing through the Gulf of Mexico. It kind of disperses into the Gulf, and as it loses its energy, it starts to first drop off the largest size grains, and then the further away you are from the mouth of the river, the finer and finer the sediment gets. So we drop this stuff off, and now we're going to bury this. We said we compact this stuff, and we're doing sandstone. So sand loses about 10 to 20% of the volume when it's compacted, and so we kind of rearrange the way that the sand grains are kind of organized or kind of stacked up. Right? There's different ways you can pack your sand, so we kind of shift it around to try to minimize the pore space as the overburden on top of it starts to grow and grow and grow, and it pushes down.
And any dad who's ever packed a trunk for a car on a trip can appreciate this. You can pack it and there's no room left, and you're like, wait a second, I can Tetris this.
Yeah,
I can pull all this stuff out of the trunk, rearrange it, and end up fitting another bag in there.
Well, because like you'll pack it perfectly, and then you'll come back to like the back door. There'll be like 3 more bags sitting there. Like, come on,
Yes.
Where did this come from?
perfectly.
Exactly. But by just based on weight and the burial, Mother Nature kind of does this for you. Just squishes it in there as best it can.
Yeah. So 10 to 20. That's not bad. It's significant. I don't know if we mentioned this during the coal episode, but coal is essentially 100 to 1. So 100 feet anthracite.
Yeah. So 99% compaction.
Yeah. So
versus now we're talking for sand, it's 10.
So sorry for bringing up coal again. The new space.
This is 5 weeks in a row now. This is just we gotta get rid of this coal thing, man.
Jesse's on his way to his dream of a coal podcast.
So all right, so we compact this stuff, and the other thing too is we want to heat the temperature up. We want to heat this up. We want to kick the temperature up a little bit, right? And the reason that this happens is because now this is where your chemistry does start to kick in a little bit. Now, we've so far been like anti-chemistry until this part, until the cementation part. We're actually cementing the grains together. We want warmer temperatures because we want chemical reactions to start precipitating these minerals out that start to fill up the pore space. So usually it's about 200 C or so is what you're looking at. Is
that temperature coming just from depth?
Geothermal grade. Yeah. So that's just from it just we're burying the stuff, we're shoving it underground, and the deeper you go underground, the warmer it gets. It's called the geothermal gradient. So we need that heat to be the catalyst for these chemical reactions to start occurring, to start precipitating out the cement that's going to glue these grains together. So the most common cements that we get with sandstones are quartz, calcite, and so iron oxide, and then sometimes clay as well. Clay's a little different. That's kind of involves.
What's your favorite?
I mean, I'm just straight up quartz guy.
I was gonna say quartz on quartz. I like
quartz on quartz. I'm a real big, Quartz Aaronite fan. We'll get into that later. Don't worry.
A pretty close second to me would be iron oxide, I think.
The iron oxide, yeah.
Iron stone.
All right, so now we have that. We should probably. I'm going to skip down to the types of sandstones.
Yeah, it's time.
It's time. Yeah. I think we.
Everyone's ready for it.
Yeah,
everyone's waiting on the edge of their seat.
All right. So we got these. First, I want to talk about these common terms. These so-called pedestrian terms of sandstone. All right.
Yeah.
So there's 3 types of these common terms of sandstone. Sandstone itself is a category of rock. All right. It's not a specific type of rock. So you can break this up into quartz sandstone, Archos, and greywacke. So quartz sandstone, this is the simplest one. We'll start off with this one. This is exactly as it sounds. It's like all quartz, like 95+% quartz. Quartz is by far the dominant mineral. This is like, we'd say this is like a very mature sandstone. Then the next type of sandstone, for the common terms, you have Archos. And Archos, depending on which definition you use, there's a couple different definitions of Archos, and the kind of, ultimately it's all the kind of the same thing. It just kind of gets into semantics, but Archos sandstone contains a fair amount of the mineral feldspar, or the group of feldspars, in that rock. So it's about 15 to 20% or so, give or take. Like I said, depending on which definition you use.
Now, would you say this tends to be like pinkish or reddish?
Yeah, I was going to say it's usually potassium feldspar, which is
usually. But I mean, you could also get the plagioclase feldspar too.
Ooh, you can shoot
Making this stuff up. So,
but in your general identification sedimentary lab, if you're identifying sandstones and it's pinkish, it's Archos.
But you can't say that. So here's the deal, because there's a lot of red quartz sandstones as well. Go out to Utah, go out to Nevada. You see these red sandstones everywhere. I think that tends to,
that would just be mean to put that in a general geology lab.
But that's real life, like, oh, life is mean. What are you going to do?
I guess. And I feel like that's how all my intro to geology lab specimens were. Like, well, this isn't right. Oh, it's magnetite. Well, this one doesn't really stick to a magnet, but it is.
Just trust us.
Yeah, exactly.
With these terms, it's the sediment. The cement doesn't matter, right?
Yeah.
Okay, I just want to make that clear.
And then you have a type of sandstone called greywacke, and that's like tends to have this like salt and pepper kind of look. Tends to be darker colored. You tend to get these. We'll talk about this in a actually. It's the next thing on the outline that we have here, but the greywackies. Well, actually, I'm going to skip for where they come from. We'll save that for the very end. But they tend to have these things called lithic fragments in it. Right. So whether it's just kind of tiny little sand-sized fragments of other rocks, or also it tends to be like dark colored minerals. We call it mafic colored minerals. Greywacke has a lot of those. They tend to be darker in color.
Is it usually poorly sorted, or does it matter?
I think it all depends. It also the sorting thing also depends on your source too. I mean, this is a topic for a whole nother podcast too. What's your source sediment coming down? Is it all the same size? Do you have a range of? So that's the one thing. If you ever defend your PhD dissertation, they're going to hit you up on that. That's one of those questions. It's easy, like
we never know.
We could spend 30 minutes on this, just tearing Chris apart.
Not that it left a scar or anything.
No, not that it actually. A friend of mine named Chris is what I should have said. Allegedly it happened. All right, so those quartz sandstone, Archos, and greywacke, those are like the three kind of like pedestrian terms, if you may. Now, since we are the premier geology podcast, I'm not going to leave you guys at the pedestrian terms. We're going to take this one up this, and we're going to go above and beyond what you guys are probably expecting, because that's just what we do here at the Flannelcast. Just under promise, over deliver. Right?
Yes, that should be our tagline.
Yes, well, or over promise, under deliver. I don't know which way you want to look at it. All right, so if you really want to get into the weeds of this, and we're not going to go too far into this, because this if we do go too far into this topic, which I don't know, we may have already, it's going to put you to sleep faster than NyQuil will. But just to kind of breeze over this, we actually have these. So those three types of sandstones we talked about are not the actual technical terms. If you really want to get into the nitty gritty, now these terms we're going to talk about, like, once again, there's like a bunch of different definitions. It all depends on whose definition you're looking at. I prefer to use this thing with, but it's called the dot classification. But it's at the end of the day, it's all pretty much the same thing. So if your sandstone is made of like 95% plus sand, it's called an Aronite. All right. And Aronite is, I didn't actually know this. I should have known this, and we were just talking about this before the podcast, but Aronite, the word arena is Spanish for sand. That's where it comes from. So it's 95% plus sand. So you have this type of sandstone called Aaronites. And then if you're about from 95 to about 50% sand, it's called a wacky. And then anything less than 50% sand is considered mudstone category. So obviously we're not even getting into we're not going to get into the mudstone stuff, but so since we're talking about the sandstones, we're just kind of going to deal with the Aronite stuff here. So a quartz Aaronite is what you should call a quartz sandstone from like more of the common term that we've used.
Yes.
So it's like 95+% quartz, or I think some even go up as high as like 98% quartz. It's like way up there. It's, for all intents and purposes, it's all straight up sand. And so these quartz sands, yes, thank you. So these quartz Aaronites, you tend to get these things forming along passive margins. So in case you don't know what a passive margin is, think of like I'm going to use the example of North America because we all live in North America. All the three Flannelcasters here, we are North Americans. You have the West Coast.
As far as anybody knows, we still don't have a room with a window.
I have a room with a window. You just on the other side of the camera.
Oh yeah. So do I. Yeah.
So what a passive margin means, you have two different types of margin: active margin and passive margin. Active margin would be like the West Coast of North America, right? We get tons of earthquake activity, strong earthquake activity. We have volcanic activity, and basically there's tectonic collision occurring along your active margins. Now your passive margins are going to be a little different. That's what the East Coast of the US is. We don't have active tectonics really occurring along the East Coast of the US. We don't have volcanoes. We don't have, regular strong earthquakes happening. It's kind of like, I was always taught, I really like this analogy. It's kind of like you have a train. So the active margin is like the engine of the train, right? The passive margin is like the caboose. It's just kind of along for the ride, getting pulled along. And so that's where along these passive margins.
Terrible analogy.
What?
That's so confusing. I don't understand. Is it still moving? Is it not moving?
It's ultimately moving. It's ultimately moving, but the active margin, that's like if anything hits it, it's going to hit the engine of the train. Boom, that first car. Smash.
Volcano. I don't. That's so confusing to me.
Yeah, I mean, it's moving in the same direction.
Yes, okay. I guess it is moving in the same direction, but it's nowhere near the front of the train.
No, I like the crazy train analogy. I'm on board.
On board.
Woo woo.
Yeah.
All aboard.
All right. So you're getting these quartz Aaronites being deposited along these passive margins, just like the East Coast of the United States or North America, or also within epicontinental seas. And so that's kind of like these shallow inland seas. The continent gets flooded out, much like the Western Interior Seaway of the Cretaceous period. What was that? What was, Jesse? You knew someone that called it the finest seaway of its day, or
the grandest seaway of its day.
The grandest seaway of its day. Yeah,
so
inside joke.
Essentially from Louisiana all the way up almost to like South Dakota.
No, even above. I mean,
it connected the Gulf of Mexico to the Arctic Ocean.
Hudson. There was a Hudson Bay arm to it.
Yeah. So there's your quartz Aaronite. It's all just like quartz size sand, and then I guess the Archos sandstone, the technical term you should actually use is feldspathic Aronite, or you could even use the wacky term if there's a little more fine grained stuff in there. So when you start to see these feldspathic Aaronites or feldspathic wacky, depending on how much, like I said, the sand content, you're dealing with something that's close to a granitic source. Think of like an alluvial fan. So an alluvial fan, you tend to see these in arid environments. There's a classic alluvial fan. Any intro to geology textbook will show the alluvial fans in Death Valley. Death Valley in California is it's the hottest place on Earth, and it's also very, very, very dry. And I think what was last year, Death Valley hit the record for the hottest spot on Earth, right?
No, hottest. I think somewhere in Saudi Arabia hit but it's the hottest in North America. You might be right.
I could have sworn we did a podcast episode about the other year. It hit the world record for the.
I had a Post-it note on my desk for a long time that literally said, "Why is Death Valley hot?"
It's because it's so dry, right?
Well, yeah, it's like the topography. Yeah, it's like its location.
I got 134 degrees in Death Valley.
The
hottest temperature ever recorded, 1913.
Don't trust that.
1913.
All right. Anyways, I think we're getting into semantics. Let's just leave it as Death Valley is really, really hot. All right.
Anyway, there's alluvial fans there because.
And so alluvial fans is just on the rare occasion when it does rain, it brings the sediment down it's very steep terrain in the mountains around there. It brings the sediment down the mountains, gravity driven, right? Water driven as well. And then once it kind of hits these like the flat lying areas adjacent to the mountains, it kind of makes this fan of sediment coming off of the mountains. That's kind of a alluvial fan in a nutshell. So you get a lot of feldspar because there's a lot of feldspar. You get feldspar in granite. So that means you're very, very, very close to a granite source. And then finally, the third type we're dealing with are lithic aeronites. So instead of saying gray wacky, you should probably say a lithic aeronite or a lithic wacky. And those tend to form nearby as well. They're not transported very far. They're formed nearby volcanic arcs. So think like the Japanese islands, the Aleutian Islands.
They're basically the fill-all. It's not feldspar and it's not quartz. It's other.
Yeah.
Basalts are basically, other.
Yeah, right, exactly. So I think that wraps it up for sandstones. Anything else that we
if you want to learn more about sandstones or if you want to talk to us behind the scenes, you could always become a Patreon member, support the podcast.
Yeah, we have some fun hangouts before and after the podcast episodes. We have some extra content we throw up on the Patreon page. We talk about some additional like news stories, just kind of additional topics, fun topics to talk about. We could do a little more rant and raving. It's a little more.
Sometimes we do a little more debating.
We do a lot
at each other,
more or less yelling at each other and just
no. We do
battle
have some
royale,
fun news stories and fun topics and stuff. But sometimes, sometimes we just have to talk about how Chris is wrong. So
sometimes we just have to talk about how Steve is mostly always wrong, and it just happens. Just happens.
It's all the mountains in Kansas can't hold me down.
Really quickly looked up temperature. We should do an episode on temperature. It depends on how you measure things. And there's all these
with a thermometer.
Well,
I'm anti-thermometer.
There's all these places that claim the hottest. Yeah. So Furnace Creek in Death Valley in 1911, but a place in Libya just like 9 years later measured 136. But and it depends on where you measure it. In Arizona, there was this group that measured it 4 inches off the soil surface, and they were getting like 160 degrees. And 4 feet, they were getting 108 degrees. So the warmest ever, the hottest ever measured using satellite data was the Lut Desert, which measured temperatures of 159.3 degrees.
See ya. Goodbye. No.
Yep, that's not human. Yeah.
No, I was at the
Lut
Hoover
Desert.
Dam, and it was 117 degrees.
Ooh.
Ugh, I can't.
That was hot.
I mean, I'm barely surviving here in Atlanta in the summertime. Hot Atlanta. And nobody actually says that down here.
To the Hoover Dam's credit, it was dry. But
it's the dry heat. 117 degrees of dry heat. Just stick your head in an oven. It's great. All right.
It is. That's the thing. It's like being inside a dry sauna. It's hot. But it's kind of bearable for a little while, and then you realize like your skin's turning red because you're slowly cooking. but it's not like that gross, like 95 and humid like you have in Philly. Like, you just want to fall over and lay on the ground.
Yeah.
But, yeah.
So I don't know if I'm probably not saying lut right. It might be loot or something, but in whatever it is called in Persian, because it's in Iran, it means emptiness plain. Yeah,
Yeah.
everyone gets cooked.
Yeah.
We're all gonna die.
Sounds like a great spot. Oh, I'm lost in the emptiness plane. This is great.
I find myself.
I mean,
often.
We're all gonna die. Flat spot was already taken.
yeah. Right next to Black Hole Alley.
Yeah. Anyway, so yeah, please become a Patreon member if you like the podcast. Please send us an email with suggestions at geologyflannelcast.com. Check us out on Twitter at GeoFlannelcast. Facebook, I'm trying to get better at that with Geology Flannelcast at Facebook. What else? Instagram. We have an Instagram.
So also, if you're interested, like how you just pause.
I thought you made a face like you were going to start talking, so I paused. Sorry.
It just the look on your face is just like you're just like you got stuck in a loop and like you had to press Control Alt Delete to get out of this.
Nice.
So yes, thank you, Maddie. One Instagram post for 5 years. Yes.
I put a post up yesterday.
I got a picture to we got to throw up there. Anyways,
Sounds like we have some Patreon volunteers that run our Instagram.
Yeah.
That's what I'm hearing.
So also, if you're interested in helping out the podcast, maybe you don't want to do a subscription per month, check out the merch we sell. You can get some stickers. You can you got some lovely Geology Flannelcast coffee mugs here, as you can see. It will
Perhaps
make
a t-shirt that
we got t-shirts
like the ones behind me.
The coffee mugs will make your coffee taste 30 to 45% better. Just saying.
At least.
It's really, I don't know what is in these coffee mugs, but it makes your coffee taste really, really good. So you should just get the coffee mugs because of that. But anyway,
it's made from the tears of angels is what it is.
You know how hard it was to find these angels?
Whew. And then to make them cry.
Oh,
Am I right?
So anyways, so geologyflannelcast.com. Also, if you want to send a listener question, every once in a while we do an episode of listener questions. We play Stump the Geologist. Twitter, do we mention Twitter? We're at GeoFlannelcast on Twitter. I think that's about it. So yeah, everyone, thanks for listening to podcasts. It's been another awesome week. We had a lot of fun doing this one.
Don't forget, it's Tell a Loved One February.
Tell a Loved One February. And happy Valentine's Day, everyone.
Yeah. I just want to say a friend of the podcast, Vince, Patreon Vince, was like, how are you not doing Flannelcast February? And I was like, but that doesn't really get the word out.
Where were you last week, Vince?
Yeah.
Come on, buddy.
Well, how we
That's
did
brilliant. Flannelcast February. We should celebrate this month.
How about we just do Flannelcast March?
It just rolls right off the tongue.
March Madness for rocks.
You have to be mad.
We should have a rock bracket.
Oh,
yeah.
All right, that's in. That is totally in. We're doing a rock bracket.
Yeah.
Oh, I can't wait. And then we'll update it every week with who won the previous week.
And as
all the way down to the final four.
So email us, go to geologyflannelcast.com.
Yes.
Shoot us an
Send
email
in
about
your favorite rocks.
What rocks you want to see in this
the
bracket.
Field of 64. It could be a rock and or mineral.
As
no. I think we should that's
the mineral can be like the Ivy League.
But
but at least one's got to get in.
There'll be a 16 seed.
Molten March. I like that. Thanks, Mark. Molten March.
Molten March.
Yeah.
But I think that's not apples to apples. It'd be like, this is like football and baseball. Like you gotta either keep it minerals or keep it rocks. I don't think that.
All right, we're gonna discuss this more off the air, but
let us
either way, we're gonna definitely have a field of 64. This is happening.
I think it's going to be easier to get 64 minerals than 64 types of rock.
I don't know. I'm pretty sure this is going to be a thing on FanDuel.
Will your mineral or rock make it into, as Maddie the Patreon said, the Flannelcast Final Four?
Ooh.
Gotta get up some jazzy music. We'll get John Tesh on a keyboard here to.
Seriously, I'm already envisioning a new design of a T-shirt. So, anyway, thank you everybody for listening. Please check us out on geologyflannelcast.com. All of our social media posts. We really appreciate you listening. And I don't know what else to say.
Goodbye.
Oh. All right. Good night, everybody.
Bye now.